Question number 6 of the worksheet, forces on threaded ring. Particle P of mass 2.1 kg is attached to one end of two light inextensible strings. So I am going to mark the weight pointing downwards, which is going to be 21 newtons because weight is equals to mg, mass times 10. Okay. The other end of the string, the other ends of the string are attached to points A and B, which are at the same horizontal level. P hangs in equilibrium at a point 40 centimeter below the level of A and B, and strings P and PB have lengths 50 and 104 centimeters respectively. Show that the tension in string PA is 20 and find the tension in the string PB. Okay. The ring is not mentioned to be smooth and it's not forming an isosceles triangle, meaning that tensions in both the strings is going to be different. Plus, it's also mentioned in the question that PA is supposed to be 20 and find the tension in string PB. That's also your hint that tension in this would be different. Let's call it T1. Tension in this would be different. Let's call it T2. And when are these two tensions same? When either it is mentioned that this ring is smooth, or if the triangle being formed is an isosceles triangle. Okay, so let's resolve the tension into its component, but for that we need some angles. There are no angles mentioned in the question, but we can find them out using SOCAT or trigonometry. I can find this angle. That's going to be sine theta. Sine theta equals opposite over hypotenuse or perpendicular over hypotenuse. So that means sine theta equals 4 over 5. Okay. I need cos theta as well. If the hypotenuse is 50 and one of the side is 40, then you can apply Pythagoras theorem to get the third side, which is going to be 50 square minus 40 square square root, which will be equals to 30. So that's 30. So that means cos 30 is going to be 30 over 50. That is 3 over 5. So this component here is going to be the one parallel to this component, and this is the adjacent component. So that means it's the cos component or the base component. So it's going to be T1 cos theta, and we already know what cos theta is. It's 3 by 5. And upwards, it's going to be T1 sine theta because it's the opposite component. Okay. Now let's talk about theta 2 or the other angle. Let's call this 1 theta 1. So all these angles, all these values are theta 1. Now let's find theta 2. So it's theta 2 over here. So again, for theta 2, we know the sine theta 2 is opposite over hypotenuse. So 40 over 104, which simplifies to 5 over 13. So I'm writing 5 over 13 here. Okay. Now again, apply Pythagoras theorem on this triangle to get the third side. So that's going to be square root 104 square minus 40 squared, which is 96. So cos theta 2 is going to be 96 over 104, which is equals to 12 by 13. Now let's resolve T2 into its components. So it's going to be this one is the component parallel to this, and that is adjacent to the angle. So that's the cos component. So T2 cos theta 2, this was theta 1 and the other one was theta 1. And upwards is going to be T2 sine theta. Okay. Now we have to find T1 and T2. Let's equate the left forces to the right forces, the up forces to the down forces. So T1 cos theta 1 equals T2 cos theta 2. That is T1 times cos theta 1 is 3 by 5. So 3 by 5 T1 is equals to T2 cos theta 2 is 12 by 13. That's equation number 1. And the second equation is going to be T1 sine theta 1 plus T2 sine theta 2 equals 21. So sine theta 1 is 4 by 5, 4 by 5 T1 plus sine theta 2 is 5 by 13. 5 by 13 T2 equals 21. Now you're going to simultaneously solve these two equations and get the value of T1, which should come out to be 20 newtons, and then find the value of T2. So we can say that T2 equals 3 into 13 upon 5 into 12 T1 and substitute it in the second equation. What is it becomes T2 equals 39 T1 upon 60. We can simplify it. 39 over 60 is 13 by 20. So T2 equals 13 by 20 T1. Let's substitute it in the first equation, second equation, 4 by 5 T1 plus 5 by 13, and then 13 by 20 T1 equals 21. Okay, so we get 4 by 5 T1 plus 5 by 20 is again 1 by 4 T1 equals 21. So we get 4 by 5 plus 1 by 4 is equals to 21 by 20 T1 equals 21. So T1 comes out to be 20 newtons. So we've shown that the tension in the string PA, which we labeled as T1, is coming out to be 20 newtons. Now find the tension in the other string. So we already have the formula for that. T2 is equals to 13 by 20 T1. So T2 is going to be 13 by 20 times 20. So T2 is equals to 13 newtons. That was question number 6. Question number 7. A small ring of mass 0.2 kgs is threaded on a fixed vertical rod. I'm going to point the weight downwards, which is 2 newtons. The end A of the light inextensible string is attached to the ring. The other end C of the string is attached to a fixed point of the rod above A. Horizontal force of magnitude 8 Newton is applied to the point B of the string, where AB is equals to 1.5 meters and BC equals to 2 meters. The system is in equilibrium with string taut and AB is at a right angle to BC. Find the tension in part AB of the string and the tension in part BC of the string. So they already told you in the question that both parts of the string will have different value of tension. Even if they had not said that, you would have known that since the triangle being formed is not an isosceles triangle. Okay. So let's call one of the tensions T1 and one of the tension T2. We need to resolve the components of T1 and T2, but for that we need angles, which we don't have. We can find theta over here, let's call it theta 1, and theta over here, let's call it theta 2, and then use it to resolve the forces T1 and T2. Okay, I'm going to find the hypotenuse first since we'll be needing it anyway. That's 2, that's 1.5 with a 90-degree in between. So this is going to be x, or the hypotenuse, it's going to be 2 square. Okay, we might not need it, but chalo, let's see. 1.5 square. Square root 2 square plus 1.5 square, it's 2.5. So this length comes out to be 2.5. Okay. Now, sine theta 2 is going to be perpendicular over hypotenuse, or so opposite over hypotenuse. 1.5 over 2.5 gives 3 by 5. So it's equals to 3 by 5. Okay. Cos theta 2 is going to be K, or base over hypotenuse, or adjacent over hypotenuse. Adjacent is 2 for theta 2. Hypotenuse is 2.5, which is equals to 4 by 5. Similarly, sine theta 1 is going to be 2 over 2.5, which is 4 over 5. And cos theta 1 is going to be 1.5 over 2.5, which is 3 by 5. Okay. Let's resolve the components of tension. This is going to be there's going to be a tension in this direction, and a component of tension is this direction to complete the triangle. Instead, I'll make the vertical one here. Okay. So this component is opposite to theta 2. So that means it's the sine component. That's going to be T1 sine theta 2. And the other one is going to be T1 cos theta 2. For the other tension T2, again, there's going to be a component in this direction, and there's going to be a downward component, which I'm going to draw here instead. Okay. Now this is opposite. The horizontal component is the opposite component. It's going to be 2T2 sine theta 1. It's not very visible. Hold on. T2 sine theta 1. I should have marked the angle with T1 theta 1 and the one with T2 as theta 2. I think I've made it more confusing. But since I've used it, I'm not going to change it. But it would have been better if T1 was with theta 1 and T2 was with theta 2. Okay. And the downward component is the adjacent component. It's the cos component. So T2 cos theta 1. Okay. And I think that's all the forces at B. Now let's resolve the forces, equate the forces. So it's going to be upward force T1 cos theta 2 is equals to downward component T2 cos theta 1. So it's going to be theta 2 was 4 by 5, so 4 by 5 T1 equals to cos theta 1 is 3 by 5 T2. Can cancel the 5s here. So it's going to be 4T1 equals 3T2. Equation number 1. And now we're going to equate the left component to the right component. So T1 sine theta 2 plus T2 sine theta 1 equals 8. Sine theta 2 is 3 by 5. So 3 by 5 T1 plus sine theta 1 is 4 by 5. T2 equals 8. Okay. So I'm going to make T1 the subject. T1 is equals to 3 by 4 T2. Let's substitute it in the second equation. 3 by 5 T1 plus 4 by 5 times 3 by 4 T2 equals 8. So it's going to be this 4 and 4 gets cancelled. So, okay, so I was supposed to replace T1 with 3 by 4 T2. So that's a mistake. So it's going to be 3 by 5. T1 becomes 3 by 4 T2 plus 4 by 5 T2 equals to 8. Let's simplify the fraction on the left. So it's going to be 9 by 20 plus 4 by 5. That gives 5 by 4 T2. That is giving me 8 into 4 divided by 5. It's giving me 6.4 newtons for T2. All right. So the tension in string T2 is coming out to be 6.4. Now let's find the tension in string T1. For that, we just use this equation. T1 is equals to 3 by 4 T2 and T2 is 6.4. So T1 comes out to be 3 by 4 into 6.4, which is 4.8. So we found tension in both parts of the string. For AB, it's T2, which is 6.4. And for BC, it is T1, which is 4.8. Okay. Next part is the equilibrium is limiting with the ring on point of sliding up the rod. Okay. So now we look at the ring. And it's saying that the ring is at the point of sliding up the rod. So it's about to move upwards. And we have to find the coefficient of friction between the ring and the rod. So if the ring is about to move upwards, that means that the friction will be pointing downwards. Let me draw the figure again here. Okay. So it's about to move upwards. That means friction is downwards. And we need the coefficient of friction. So I'm writing mu r here. And also downwards is the weight, which is 2 newtons. Okay. Now tension in this part of the string was T2, which came out to be 6.4. So now we're going to make it point away from point A, because tension is always pointing away from your reference point. So this is the tension, and which is 6.4. Okay. So this component is going to be parallel to this component, which is the cos component. That angle was theta1. Sorry, the sine component, because the opposite component is sine component. So it's going to be 6.4 sine theta1. And this upward component is going to be the adjacent component. So cos 6.4 cos theta1. Okay. Also, the normal contact force would be, here's the contact, here's the pull because of the tension. So the contact is going to be here, so R is going to be here. So that's an R. Okay. Now we have to find the value of mu R. So let's equate the up and the down forces. This is part 2. Up force is 64 cos theta1 equals down forces are mu R and 2. So 64 cos theta1 is 3/5 is equals to mu. R is the left force, which is equals to the right force, 6.4 sine theta1. Plus 2. So it's going to be 64 into 3/5 is 38.4 is equals to mu 6.4. Is it, was it 6.4 here as well? So it's going to be 6.4 into 3/5, which is 3.85. Sorry, 3.84. Okay, 66.4 into sine theta1 is 4/5 plus 2. It's going to be 6.4 into 4/5 is 5.12. Plus 2, send plus 2 to the other side, 3.84 minus 2 divided by 5.12. It's giving me 23 upon 64. Which is the correct answer. Okay, you may leave it as a fraction or you may give it as a decimal, which is coming out to be 0.359 in three significant figures. Any questions here? Okay. If not, then we start the next question, question number 8. Here's the question, and the figure is okay. The ring of mass 4 kg. So 4 kg means a downward force of mg, which is 40 newtons, is attached to one end of a light string. This string is threaded on a fixed horizontal rod and the string is pulled at an angle of 25 degrees below the horizontal. With the tension of the string, with a tension in the string of 10 newtons, with the ring in equilibrium. Equilibrium means it's not moving. That means forward forces equals to backward forces. Find in terms of T the horizontal and vertical component of the force exerted on the ring by the rod. Okay, so vertical and horizontal components of the forces exerted on the ring by the rod. Okay, so there's going to be a normal contact force exerted on the ring by the rod. It's going to be in the upward direction. And then there's going to be a frictional component, which since the pull is towards the right, so when it moves, it'll be moving towards the right. So in this direction, you have mu r or friction. Friction. Find in terms of T. So you have to give these components in terms of T. Okay, so let's do that. For that, we'll have to resolve the tension. Tension is this direction, is going to be the cos component. So T cos 25. And then in this direction, it's going to be the opposite component. That is T sine 25, but I'm plotting it here. T sine 25. Okay. So R, the upward force, equals to the downward forces, which are T sine 25 plus 40. And friction is equals to T cos 25. So that is going to be the answer for part 1. Let me check. T cos 25 and T sine 25 plus 40. Okay. Part 1 is correct. Part 2, the coefficient of friction between the ring and the rod is 0.4. So we're given the value for mu. Given that the equilibrium is limiting, find the value of T. So now for part 2, we'll replace friction by mu r equals T cos 25. Mu we know is 0.4 and R we know is T sine 25 plus 40. equals t cos 25. Okay. Now we're going to move the t terms on the same side so that we can take t common. Going to be 0.4 t sine 25 minus t cos 25 equals to, we get negative 0.4 into 40. I can take t common. So 0.4 sine 25 minus cos 25 equals minus 16. What is 0.4 into 40? Yes, 16. Okay, now tension equals minus 16 over 0.4 sine 25 minus cos 25. $21.7019, which rounds off to 21.7. Any questions here?
No,
Okay.
no, ma'am.
Then we do question 9. A ring is threaded on a fixed horizontal bar. The ring is attached to one end of a light and extensible string, which is used to pull the ring along the bar at a constant speed of 0.45 meters per second. Constant speed means acceleration is 0. And also for constant speed, you use the formula speed is equals to distance over time. You don't use equations of motion because acceleration is 0, and you use the simple formula speed is equals to distance over time. The string makes a constant angle of 24° with the bar, and the tension in the string is 6 newtons. Find the work done by the tension in the period of 8 seconds. Work done will be addressed in later chapters. And for now, you need to know that the work done is equals to force in the direction of work times D. इसे कराना ही नहीं चाहिए. I think let's not do this right now. This will come up again when we do the chapter on work done. Instead, let's do question number 10. Okay. Smooth ring R. So if the ring is smooth, that means the tension in both parts of the string should be the same. So in this direction, it's going to be T, and this direction is going to be T as well. Okay. The mass is 0.16, so that means the weight downwards is going to be 1.6 newtons, mg. Is threaded on a light inextensible string. The ends of the string are attached to fixed points A and B. A horizontal force of magnitude 11.2 Newton acts on R in the same vertical plane as A and B. The ring is in equilibrium. The string is taut with angle ARB equals 90 degree, and the part AR of the string makes an angle theta with the horizontal. The tension in the string is T newtons. Find two simultaneous equations involving T sine theta and T cos theta. Okay, so we can easily resolve the upper force, this component, and this component. Okay, and this component I've brought from here. So this is the adjacent component, which is the cos component. So T cos theta, and this one is the opposite component. So T sine theta. Okay. Now we have to resolve this force. But the problem here is we don't have the theta. We need a theta here or we need a theta here. If we have any one of these theta, we'll get a right angle and we'll be able to resolve the two components of T. Okay. But look at the setup given to us. There's a theta here, and then there's a 90-degree angle here. And if you draw a line here, that would be theta as well from alternate angles. And this would be 90 minus theta. Now, this is going to be 90 minus theta. But let's not take 90 minus theta because we'll have to do sine 90 minus theta, cos 90 minus theta. Will be complicating it. Instead, let's take this angle here. I'm going to find this angle. So that's 90 as well. So the sum of all these three angles should be equals to. So the sum of these three should be equals to 180. So if we do that, x plus 90 plus 90 minus theta equals 180. So then this 90 and 90 adds up, cancels with the 180. You get 90 minus theta. Sorry, x minus theta is equals to 0. So x is equals to theta. So this angle here is actually theta as well, same as this angle. We've proved it. So this angle is theta as well. So now we can resolve this t into its component. One is going to be a component is this in this direction, which is the opposite component. So it's the sine component now. It's going to be t sine theta. And the other component is going to be downwards, which I'm going to instead plot over here, which is going to be t. It's the adjacent component, so t cos theta. Okay. That is the resolving of the forces is done. Now let's form two simultaneous equations involving t sine theta and t cos theta. So we have t sine theta, which is the up force, equals to t cos theta plus 1.6. That is one of the equations. Okay. And now we're going to equate the left and the right forces. So again, we have t sine theta plus t cos theta equals 11.2. Okay. I'm going to rearrange the first one. It becomes t sine theta minus t cos theta equals 1.6. Add these two. This gets eliminated. You have 2t sine theta equals Okay, this was the answer for part one. I started part two haphazardly. This is the answer for part one. For part two, you have to solve these simultaneous equations. Okay, so we're getting t sine theta equals 11.2 plus 1.6, which is going to be 0.8 and 12.8. That's going to be the equation number one. Next, I'm going to find t cos theta. Okay, for that, I'm going to use the same simultaneous equations again, but this time I'm going to multiply the second one with negative one. So negative t sine theta plus t cos theta equals negative 1.6. So now the cos component, sine component gets eliminated. We have, so this comes out to be t sine theta equals 6.4. This comes out to be 2t cos theta equals what is 11.2 minus 1.6, which is 9.6 divided by 2, that's 4.8. So t cos theta equals 4.8. Now we have t sine theta, t cos theta. We can find the value of theta and t from here by either applying Pythagoras theorem on t sine theta and t cos theta, or dividing them and getting tan theta and then taking tan inverse. It's up to you. So I'm going to divide them and get tan theta. So t sine theta over t cos theta equals 6.4 over 4.8. So t and t gets cancelled. We have tan theta equals 6.4 over 4.8. It's 4 over 3. Tan inverse 4 by 3 is 53.13. So theta comes out to be 53.13. Okay, rounded off to 53.1. And then to find t, put it back in any one of t cos theta or t sine theta. I'm going to use t sine theta equals 6.4. So t sine 53.1301 equals 64. T will be 64 divided by sine answer, which is 80. Sorry, it was 6.4, not 64. 6.4, 6.4, so it comes out to be 8 newtons, not 18 newtons. Okay, so that's the answer for question number 10, part 2. If you have any questions, please ask.
No questions, ma'am.
Let's start the pure paper now.